Hey guys! In this video we're going to talk about limits. Now in the last video we kind of introduced the idea behind a limit, but now we're actually going to talk directly about it. So the easiest way I know of to understand a limit is with a graph. So using this lovely first example, let's take a look. So this is our graph. And they want us to find the value of the graph at x equals 1. So if you notice here, if you go to x equals 1 and then go to the graph, we actually have a open circle. This means that there is a hole. Open circle is a hole in the graph. So there's no point there. It gets close, but at f of 1, it's not there. Now, if you look up, you'll see a solid dot. This is the actual point of f of 1. So we jump from the hole to that lovely point there. So the f of 1 is, well, the actual point occurs at y equals 3. Okay? However, the limit as x approaches 1 of the function is not 3. I mean, the actual point is 3, yes. But the limit, well, that's where the hole is. Because that's where it looks like it's going to be. So a limit is a little bit like an asymptote being a line that you approach but never actually touch. So limits are things that you get really close to, but you don't actually hit. So the limit as we approach 1, but we don't hit 1, is -3. As soon as we actually hit 1, that's something else. But the limit as we approach 1 goes with the graph, which goes with the hole, so it's -3. Okay? So when you're talking about holes versus actuals, that is what you're talking about. But a lot of the time you're actually talking more along the lines of non-hold things, normal graphs. So for f of 0, we would have -4, right? F of 0 there and -4 there. And this is a continuous graph here. It doesn't stop, and there's no hole at x equals 0. So the limit of as x approaches 0 is the same as f of 0. In most cases that will be true, but not all cases. So do be careful. Okay, a lot of these limits, we had to come up with the word limit to talk about things because we had these weird discrepancies that could happen. So one way to think about this is that the limit as x approaches some number a of a function f of x may not equal f of a, which is what we see here. F of a is 3, but the limit as we approach f of a is, well, it's not 3. So be careful. As we go through these sections, we'll get different things that we can add to our list of limit properties and limit conditions. So here's the first one. Okay, so let's look at our next example here. So the function value, so y, when x equals 3, well, there's a hole there, right? And I'm looking up and I'm looking down and I don't see a solid dot. So there's no actual here. There's just the whole. So our function, when x is 3, is dne. That is, does not exist. Does not exist. Also sometimes known as undefined. Both would be correct. But the limit does exist. The limit will actually always exist. So even if we can't find the function value, we can still talk about the limit. So the function value, the limit, as x approaches 3. Now this says x approaches 3 from the left. So to indicate this from the left part, we would say x approaches 3, and then we would have a little bitty minus sign in that top corner to indicate that it's from the left. Okay, so the limit as x approaches 3 from the left of f of x equals. So as we come from the left, we're looking at the graph itself, the dark line, and that would be the limit from the left, so we get closer and closer to 3, and that would be 0. Okay, good deal. So the next would be as we approach 3 from the right. Okay, so as we approach from the right, so we would have a little bitty plus sign in that top corner of the 3 for the from the right part of f of x. So from the right, and we go and go and go, and that is 0 again. So we can assume the limit as x approaches 3 in its entirety of that function will be 0. And part of how we know this is because as we approach from the left and as we approach from the right are the same number. If they were different numbers, we would have a problem. But since they are the same number, we can say this is true. Okay? So, let's write this down. If, and only if, one way to write this is IFF, if and only if. Mathematicians are a group of people that are covered in abbreviations, and we got lots of them. So, if and only if the limit as x approaches a from the left is equal to the limit as x approaches a from the right, then we can say that the limit as x approaches a is whatever that limit is. These two limits must be the same number. Let me rephrase this. So, let's say these both are L. As long as they are the same L, then the limit as we approach the number is that L. But if they're not, then we have a problem. So let's have an example. Let's say we have this lovely piecewise function here. So our function is v of h, and we have h of -2. So holes are the open circles, and dots are the actuals. So v of -2 is the solid circle here, which would put us at 1. Okay, good deal. So the limit as h approaches -2 from the left, that little negative symbol there, that one means from the left, as opposed to this lovely plus, which is from the right. So as we approach from the left, so from this way, going that way, the limit as we follow this lovely graph would also be 1. All right, getting closer and closer to 1 there, so that works great. But we have this lovely jump, and if we go the limit as h approaches -2 from the right, so going this way, going this way, going this way, that is, well, it's not 1, is it? That's 5. So because our limit from the left does not equal our limit from the right, the limit at that number does not exist. They have to be identical for us to say that the limit at the number itself as a whole is that same number. So be careful. We have different things that we can use to talk about, but there are properties that we must follow. So the limit as x approaches a is not necessarily the same as f of a, but the limit of the left must equal the limit of the right for the limit of the whole to exist. Okay, so let's do this lovely thing. Use a graph and a table to estimate the limit of g of x as x approaches 0 when g of x is that. So, I would definitely use your calculator. Make it easy on yourself. Use your calculator to graph it. Be careful of your parentheses, that you type it in correctly. You'll need parentheses around your entire numerator here so that your calculator reads it correctly. So it would look something along the lines of parenthesis e caret 4x minus 4x minus 1 close parenthesis, and then divide by x squared, or x caret squared. And that would be in your y equals. So if we do that, we're going to get a graph that looks something along these lines. And we will have a hole and something like that is what our graph will look like. Adjust your window to help you see it more clearly. Okay, so this means that the limit as x approaches 0 of our lovely function is going to be approximately, these wiggly equals sign, it means approximately, so that's going to be approximately 8-ish. Now, we say approximately because we're not sure. I mean, it's all fine and dandy to make our calculator do the hard part, but it's still an estimation because we can't really zoom in enough to get more than an estimation. So if we want something a bit more accurate, we're going to use a table. So we'll move that a bit. And let's go to a table. So an x and then g of x. And we are going to get closer and closer to what we think is correct. So 0 is going to be what we're looking at. So 0 in the middle. And let's do 3 on each side just to make sure it's as good as possible. So this means that There we go. So as we approach 0 from the left, so as x approaches 0 from the left, it must equal the same thing as x approaches 0 from the right. Okay? Must be the same number. If it's not the same number, we're in trouble. So here's where we go. And just use your calculator as you input the lovely x's to figure out what g of x is. So, let's see here. Negative 0.1. And in this case, make sure that your denominator x has a square on it as well, so that your calculator doesn't accidentally think that the square is somewhere else. So we have 7.0320, 7.8944, 7.9893. So it is actually approaching the limit as x approaches 0 from the left. Does look pretty good. Does look about 8. Alright, good deal. So now we must confirm that it's the same way as x approaches 0 from the right. So 0.1 is 9.1825, 0.01, 8.1077, and 0.001 is 8.0107. So this does indeed look good. So if the two sides are equivalent and equal, then we can say with alacrity that the limit as x approaches 0 in its entirety is 8.